Psychology. Oh, okay. Very nice. Okay. So again, you're probably not going to use Gen Chem for the most part, except for maybe Chad because he has chemistry. But for the most part, a lot of you guys will do like OChem and stuff, which gets really hard. I think Gen Chem's pretty much like a weed out class. Like whoever can survive it can survive for pre-pharmacy. Nice. My sister's a pharmacy. She's in pharmacy school right now at UGA. So I know what you're gonna go through. And let me tell you, you have to memorize a lot of drug cards. But anyways, let's just get into it. Okay, so how was the quiz today? Because I did the what's it called? If you went to the session yesterday, I had not answers, but like that last slide, like the bonds and stuff, was supposed to help you with the quiz today. Did it help? Yes, no. So I would know in the future. Good, good. Okay, because if you went to my last session, I put stuff on there like bond energy and stuff and how to do it. Because I saw the quiz. Yeah, so because I saw the quiz 12 before you guys had it. So I took what I saw because I saw the 4 possible questions and then I made my SI thing based off of that. So that's why I always like for kids to go to sessions because I make my sessions based off of what will be quizzed on later. So you're gonna need it anyways. Anywho. Let's get into the agenda. Today I'm going over 4.4, 5, and 6. Unfortunately, for 4.7, 4.8, you guys have to learn that by yourselves. And then my review session, I'm gonna do the whole chapter. And it's gonna be kind of long. So I won't have an essay session on those because I only have one that week. So again, like if you have time, go to this essay session because I'm not gonna be giving out PowerPoints this time because and when I do it, it's always like 20, 30 kids who never come, who always ask. So, I mean, of course, there's always kids like you who always ask, and that's fine. But then there's kids who never go, and they're like, oh, can I have it? And it made no sense. So, I'll only give it to kids who I know either went to this session or kids who I know always go. Because then I know you utilize the time with SI. Anyways, so we're gonna get into that, and then we're gonna do a blast from the past. So I'm gonna go over parts of chapter 4, all the way from 4.1 to 4.3, and go over all of that to see like what you remember, what you know. Because if you don't know it now, you're gonna have to know it for Friday. So let's do a warm up. What are the different molecular forms of the same element? And this was in your 4.4, I believe. So what is that? What's the different molecular forms of the same element? Does anyone know? Like resistance? Okay, I figured someone would say this. There's a specific term though that I'm looking for. Because the next one is what is the resistance structure? So what's the different molecular forms? I'm looking for a specific word it refers to. And I'm just testing you guys over vocabulary, so you have questions over this, you know what that word means. Because I bet most of you only know the word like resistance, and then that's it. So does anyone know what that is? I think it was in your reading. Do we know? If you don't know, you can just say, I don't know. It's okay. Nope. Okay. It's called... Anyone? You forgot? Okay. It's allotropes. That's what it's called. Allotropes. Again, very, very similar to resistance ones. Yeah, I spelled it wrong. But allotropes. What about a resistance structure? I bet you guys know that one. So what's a resistance structure? That's pretty easy, right? Don't worry. It takes me a long time to do SmartWorks too, by the way. So you don't feel bad. It takes me over an hour too. What's a resistance structure? Does anyone know what that is? Right, it's pretty easy. So we have one thing of like carbon to carbon, and we have multiple things like that. What is that? Like, how do we explain that into words? What's a resistance structure? So that's a resistance structure, right? But that's visually. How do we say it verbally or write it out? What's a resistance structure? Chemical bond. Having multiple bonds. That's not the right word, I'd say. Resistance structure means having the same arrangement of atoms but different arrangement of molecules or bonding pairs. So you're gonna have the same elements, like you both have CC, right? But the bonding pairs are completely different. It's gonna be like that all the time when you have like O is bonded to O or N or whatever, but you have to have an octet. What happens usually is that you'll change the bonding pairs. The atoms stay the same. It's the same arrangement of atoms, different arrangement of bonding pairs. That's all you need to know. Same arrangement of atoms, different arrangement of bonding pairs. That's resistance. What about delocalization? The D should help you a little bit. That sounded kind of weird. But what about like the prefix and stuff? What does that mean? Delocalization. It has to do with electrons. What do we know about this? Yes, exactly. See, you remember some stuff. Electron density spread out, exactly. And is it over one atom or is it over several atoms? Delocalization. Because we know it's electron density, right? Many, yes, exactly. It's over several different atoms. Many, exactly. So speaking of delocalization, yep, exactly. So what's the key point of delocalization? Because you're not going to use it on a test, like, oh, you know delocalization, okay, and what? What's the key point of delocalization? Like, what does it do to an electron? Or to an atom? What's the point? Like, okay, so it has electron density, so what? Like, what's the purpose? What's the objective? Because she's not going to ask you that on a test. So what's the key point of delocalization? Does anyone know? Because it's spreading out that density, right? But what about it? What does that do? What's the effect of that? Do we know? If you don't, it's okay. You can just give your best guess. You don't know. Okay, so if you have multiple atoms like this, and the electron density is all spread out and stuff, does it increase it? Actually, it's the opposite. And what it does, actually, because you're spreading it out, it lowers the potential energy. Because you spread it all out now. And it also decreases the energy of that molecule as well. And speaking of that, what is that called? When you increase the potential energy and you decrease the the energy of a molecule, what's that called? Goes in with the key point of delocalization. No idea. You guys have to brush up on vocabulary. Like this happens like every SI session. It's actually called yes, Chad, you're correct. Yes, that's correct. Finally, yes. Okay, yes. Resistance stabilization. That's completely correct. And did we get that? Because it stabilizes it. Because it's taking that electron density and it's putting it out over several atoms. So it decreases that potential energy and it decreases the energy in general of the whole molecule. Did we understand that? Yes? Okay, nice. If you're having trouble with this, I don't mind sending out this PowerPoint at the very end. You guys want? So yeah, these are just the answers. I think we're good on that. So, practice problems. Draw the resistance structures of nitrogen. So what's the first step? What do we do first? Does anyone know? NO3, and this is like the same steps every time. Like I know this seems very like tedious. Like, oh, you have a nitrate, you have a azide, and you have a nitronium, but it's all the same steps. Like, what's the first thing you do? Does anyone know? When you're making a resistance structure. Count. Yes, exactly. Yes, so you count the valence electrons. Very good. So what is this? What about N? What's the valence electrons of N? It's in group 15, right? So what's that? 5, yes, exactly. And what about, yes, and then 2, no, not yet, but oxygen is how many? It is right next to nitrogen, so what is that? 6. Yes, resistance structures are the same as Lewis structures. It's just different variations of a Lewis structure for that ion. It's pretty easy. Like once you see it, you'll get it. Especially after this, I bet. And because it's minus here, what do you do? Dr. Kelly never really went over this section in depth, and I think it's gonna come back and bite you guys later when you take a test. But NO3, like if you have a minus sign, what do you do to it?
Oh,
You add it, yes, exactly. So now you're gonna add 1, so when you get that, you get 23 plus 1, which is 24, yes. So when you do that, here, I'm gonna draw this out, because I know it's probably difficult for you guys to draw it anyways. So I'm just going to do it for you because it's a Friday. So when you do that, and you just do it the regular way, single bonds, what do you notice? So I'm writing it here. What do you notice about it? Like something's off. What's off about it? Like why would this not work? Ignore that. Why would this not work? Like what's missing? So you're looking at this. What's missing about it? What's wrong? Because there's 24 valence electrons, so why is it not correct? What's wrong about that? Yes, exactly. It doesn't have a full octet yet, right? N only has 2, 4, 6. You need 8, right? So what do you do instead? Does anyone know? Because these will have all single bonds. Make a bond. What kind of bond essence? Because these are all bonds, right? These are all single bonds. What's the problem? Right? Because you need an octet, but this only has 3. 3 single bonds. What can we do that would not change the valence electrons? Double bond, yes, correct. So you would change one of these. Yes, exactly. Make a double bond. So that would be 2. That one's 1 and 1. So now it's correct. It's full. Now, but what about, because this is already correct. Now we've determined that that's done and over with, right? But how do you make a resistance structure out of that? So this is the correct version of it. How do you make a resistance version of it? It's really fast and really easy. Like once I tell you guys, you're gonna be able to do this like back and forth. Like it's not difficult. But does anyone know? No. Yeah. Instead of you. Yes. Okay. Yes, Akash, you're completely right. I think some people, if you didn't know it, I think again, Dr. Kelly didn't really go over this enough. And I think it's because she gives you guys quizzes at the beginning and it takes up too much time. And then on top of that, when she teaches it, she doesn't go over it enough. And I think that's why so many of you guys are confused. And that's why I think only Akash knew it. Or maybe a few people knew it. But yeah, Akash is. I mean, it's true. I mean, I love Dr. Kelly. Don't get me wrong, but like, I'm gonna give credit where credit's due. Yes, like someone said, like licking this morning or whatever. It's not that type of class. But yes, this is how you do the resistance structures. So for N, you can switch up the double bond from here to the right, or you can put it on top and have N have 2 single bonds on the sides. It is on the left, but you can also put it on the right and you can put it on top. That's what makes a resistance structure. It's having multiple different versions of that original Lewis structure. So any one of those could work. Yeah, you can just switch them around. As long as they all equal 24, you can switch around that double bond. And that's what makes it a resistance structure because they have the same arrangement of atoms. Like N is still in the middle. The oxygens are all still like on the outside. The only difference is the bonding pairs. The bonding pairs are in a different order. Do you get what I'm trying to say?
Mm-hmm.
Yeah, double bond is 4 because 1 is just 2. So having a double is 4. And I wouldn't call it 4 valence electrons. It's more like 4 just ions, really. Okay, so if you're not getting it, you'll see when I show you the picture in a little bit. So I'm gonna. Okay, does anyone have any questions on that so far? Like, what's confusing about it? Do you have any questions? Like, what don't you understand about that? Because the N is gonna be the same. The N, the O, the O, the O, like they're all gonna be the same thing. The only thing that will change are the bonding pairs. That's it. That's the only thing that will change from this. Do we understand that? At least? Yes? No? If you understand, you can raise your hand. Okay, wait, let me see. I think some people had on the double and triple bonds. Again, you're just moving them around. I understand how you get the number of valence electrons, but I don't understand them. Okay, we'll go over them. Yeah, I have more stuff on that here. So let's do the second one. So, valence electrons first. N3 negative, what is that? Because we have 5, right? 5 times 3 negative, right? So you're going to add 1,
16.
which is 16, right? So when we're doing this, you have N N, and N. So we're gonna do, so when you do this regularly, and you're doing a regular Lewis structure, this one's just a regular one, right? A regular structure, nothing like crazy about it, it's just a regular structure. What do we notice about it? Like this so far? What's wrong with it? It's the same thing as the other one. Like, what's confusing about it? Does anyone know? Because the ends on the outside have 8, right? But the one on the insides, yeah, the middle one doesn't have an octet. It only has 2, 4, right? So what you have to do is make a double bond. So what you're gonna do is you're gonna take out this and you're gonna create that double bond. Bam. So now it's perfect, right? It's great. But there's a different version you can also do. Because you can do 2 here, right? But you can also do 3 on this side. And you can do 1 on this side. You see how they still match 4, but it's a different order? Do you see how it's all 4? Like, that's 2 and 2. Like, it's all 4 bonds. The only difference is that there's 3 on one side and there's 1 on the other. Yeah, exactly. And then the last structure is just 1 on this side and then 3 on the other side. Are you guys getting it? Like, it's the same structure again and again and again. You're just switching around stuff, like the bonding, like the little lines. That's pretty much it. You're just switching the lines between them. Yes, Chad?
Okay, so if there's like multiple numbers of the same element, it doesn't matter like what order you put them in, right?
As long as you get the final